Carbon capture and utilization, or CCU, represents a critical suite of technologies designed to address the escalating challenge of atmospheric carbon dioxide concentrations. These processes are engineered to capture CO2 emissions from various sources and subsequently repurpose this captured carbon for diverse applications. The overarching goal is to transform a waste product into a valuable resource. CCU technologies are not merely about sequestration, they actively seek to integrate CO2 into industrial and commercial value chains. This approach distinguishes CCU from carbon capture and storage, which primarily focuses on long-term geological sequestration without subsequent utilization. The scope of CCU is broad, encompassing both the capture mechanisms and the subsequent conversion or application pathways. The primary sources for CO2 capture within CCU frameworks are diverse and widespread. Industrial facilities such as cement plants, steel mills, and chemical production sites are significant emitters of concentrated CO2 streams. Power generation facilities, particularly those relying on fossil fuels, also represent major point sources for capture. Beyond these stationary industrial sources, CCU also encompasses technologies capable of extracting carbon dioxide directly from the ambient air. This direct air capture, or DAC, offers a pathway to address diffuse and legacy emissions that are not tied to specific industrial stacks. The versatility in capture sources underscores the comprehensive nature of CCU. The fundamental purpose of CCU is multifaceted. Foremost, it aims to significantly reduce greenhouse gas emissions, thereby playing a crucial role in mitigating climate change. By preventing CO2 from entering the atmosphere, CCU directly contributes to global decarbonization efforts. Secondly, CCU endeavors to create new economic opportunities. By converting captured CO2 into marketable products, it fosters innovation across various sectors, from energy to manufacturing. This economic incentive can help drive the adoption and scaling of these technologies. Ultimately, CCU is positioned as a vital component in the global strategy to transition to a low-carbon economy. It offers a pathway not only to reduce emissions, but also to establish a more circular carbon economy, where CO2 is viewed as a feedstock rather than solely a pollutant. Its role in achieving climate targets is increasingly recognized by scientific and policy communities alike. Carbon capture methodologies are broadly categorized based on the point in the industrial process where CO2 is separated. Each method presents distinct advantages and challenges, tailored to specific emission sources and operational contexts. Understanding these distinctions is crucial for effective CCU deployment. Post-combustion capture is perhaps the most widely studied and implemented method. In this approach, CO2 is captured from the flue gas after the fuel has been combusted. This means the technology can be retrofitted to existing power plants and industrial facilities without significant modifications to the primary combustion process. The flue gas, typically at atmospheric pressure and moderate temperature, contains a relatively low concentration of CO2, often mixed with nitrogen and other gases. Amine-based solvents are commonly used to selectively absorb CO2 from this gas stream. The CO2-rich solvent is then regenerated, releasing a concentrated stream of CO2 for utilization or storage. Pre-combustion capture, in contrast, separates CO2 from the fuel before combustion occurs. This method is typically integrated into processes like coal gasification or natural gas reforming, where a syngas, a mixture of hydrogen and carbon monoxide, is produced. The carbon monoxide is then reacted with steam to produce more hydrogen and CO2. This CO2 is captured at high pressure and concentration, making its separation potentially more energy efficient than post-combustion methods. Pre-combustion capture is often associated with integrated gasification combined cycle, or IGCC, power plants, which are designed for high efficiency and low emissions. The resulting hydrogen-rich fuel can then be combusted to generate power with minimal CO2 emissions. Oxy-fuel combustion represents a third distinct capture strategy. In this process, fuel is burned in an atmosphere of nearly pure oxygen rather than air. This eliminates nitrogen from the combustion process, resulting in a flue gas composed primarily of CO2 and water vapor. The water vapor can be easily condensed, leaving a highly concentrated stream of CO2. This concentrated CO2 stream simplifies the subsequent purification and compression steps, potentially reducing the energy penalty associated with capture. Oxy-fuel combustion requires an air separation unit to produce the pure oxygen, which adds to the system's complexity and cost. Direct air capture, or DAC, stands apart from the other methods as it extracts CO2 directly from the ambient atmosphere. Unlike point source capture, DAC is not tied to specific industrial emissions, but rather addresses the diffuse CO2 already present in the air. This makes it a potential solution for removing legacy emissions and achieving net negative emissions. DAC technologies typically involve large fans that draw air over chemical sorbents or solvents that selectively bind with CO2. Once saturated, the sorbent is heated or depressurized to release the concentrated CO2. While DAC offers significant potential, it faces challenges related to energy intensity and cost due to the low concentration of CO2 in the atmosphere. Once carbon dioxide has been captured, its utility is realized through various utilization pathways. These pathways transform CO2 from a waste product into a valuable feedstock, contributing to a circular carbon economy. The choice of utilization pathway often depends on the purity, quantity, and pressure of the captured CO2, as well as market demand. Enhanced oil recovery, or EOR, is one of the most mature and commercially deployed CO2 utilization methods. In EOR, captured CO2 is injected into mature oil reservoirs to increase crude oil production. The injected CO2 reduces the viscosity of the oil and increases reservoir pressure, allowing more oil to be extracted. While EOR can significantly boost oil recovery, its environmental benefit is debated. The CO2 is typically stored underground during the process, but the ultimate climate impact depends on the life cycle emissions of the produced oil. Careful accounting is required to ensure a net reduction in atmospheric CO2. The production of fuels and chemicals from captured CO2 represents a highly promising area of research and development. CO2 can be catalytically converted into synthetic fuels such as methanol, methane, and even longer-chain hydrocarbons. These e-fuels can serve as drop-in replacements for fossil fuels, offering a pathway to decarbonize transportation and industrial sectors. Beyond fuels, CO2 can also be transformed into a wide array of valuable chemicals. These include polymers, plastics, urea for fertilizers, and various organic compounds. The chemical conversion of CO2 often requires significant energy input, typically in the form of hydrogen, which ideally should be produced from renewable sources to ensure a net environmental benefit. The construction materials sector offers another significant opportunity for CO2 utilization. Carbon dioxide can be incorporated into the production of concrete, a material with a substantial carbon footprint due to cement manufacturing. Technologies exist to cure concrete with CO2, which chemically binds the CO2 within the material, enhancing its strength and durability. Furthermore, CO2 can be used in the production of aggregates and other building components. This approach not only sequesters CO2, but also potentially reduces the overall carbon footprint of the construction industry. The long lifespan of buildings means that CO2 stored in these materials can be effectively sequestered for decades or even centuries. The food and beverage industry has long utilized CO2 for various applications. The most common use is for carbonation in drinks, where CO2 provides the effervescence in sodas, beers, and sparkling waters. This application requires high-purity CO2, often sourced from industrial processes or fermentation. In agriculture, CO2 is used in greenhouses to enhance plant growth. Elevated CO2 concentrations can significantly boost photosynthesis, leading to higher yields and faster growth rates for various crops. This application demonstrates a direct biological utilization pathway for captured CO2, contributing to food security. The benefits of carbon capture and utilization are extensive, spanning environmental, economic, and systemic impacts. These advantages underscore CCU's potential as a multifaceted solution in the global effort to combat climate change and foster sustainable development. Recognizing these benefits is crucial for driving investment and policy support. From an environmental perspective, CCU offers a direct and significant pathway to reduce CO2 emissions from industrial processes and power generation. By capturing carbon before it enters the atmosphere, CCU technologies directly contribute to lowering the overall concentration of greenhouse gases. This is particularly vital for hard-to-abate sectors where direct electrification or renewable energy integration is challenging. The reduction in CO2 emissions directly contributes to climate change mitigation efforts. By preventing further warming, CCU helps to limit the adverse impacts of climate change, such as sea level rise, extreme weather events, and ecosystem disruption. It provides a necessary tool alongside renewable energy deployment and energy efficiency measures. Economically, CCU fosters innovation across a diverse range of sectors. The development and deployment of capture technologies, CO2 conversion processes, and new product markets stimulate research and development. This drives technological advancements and creates new intellectual property. Furthermore, CCU creates new economic opportunities by establishing entirely new industries and value chains. The production of synthetic fuels, chemicals, and building materials from captured CO2 generates jobs and stimulates economic growth. This can help diversify economies and build resilience in regions transitioning away from traditional fossil fuel industries. CCU also plays a pivotal role in advancing the concept of a circular economy. By transforming CO2 from a waste product into a valuable resource, it promotes resource efficiency and reduces reliance on virgin materials. This paradigm shift encourages industries to rethink their waste streams and integrate them into productive cycles. The production of valuable products from captured CO2 can potentially offset the costs associated with carbon capture. This economic feedback loop makes CCU more financially viable and attractive for industrial operators. As markets for CO2-derived products mature, the economic incentives for CCU are expected to strengthen, driving further adoption. Despite its promising benefits, carbon capture and utilization faces several significant challenges that must be addressed for widespread deployment. These hurdles encompass technological, economic, and environmental considerations, requiring concerted effort from researchers, policymakers, and industry stakeholders. Overcoming these challenges is paramount for CCU to fulfill its potential. One of the most substantial challenges is the high cost associated with CCU technologies. Carbon capture processes, particularly those involving chemical absorption, are energy-intensive and require significant capital investment for equipment and infrastructure. The operational costs, including energy for regeneration and compression, also contribute to the overall expense. The economic viability of CCU is often dependent on carbon pricing mechanisms or subsidies that incentivize emission reductions. Without sufficient financial incentives, the added cost of capture can make CCU-equipped facilities uncompetitive compared to those that continue to emit CO2 freely. Reducing these costs through technological innovation is a key research priority. Another challenge lies in the variable efficiency of different CCU technologies and their applications. Capture efficiency can vary significantly depending on the CO2 concentration in the flue gas, the specific capture solvent or sorbent used, and the operating conditions. Lower efficiency translates to higher energy penalties and increased costs per ton of CO2 captured. Furthermore, the efficiency of CO2 utilization pathways also varies. Some conversion processes are highly energy-intensive, requiring substantial inputs of renewable energy to be truly carbon negative. Optimizing these processes for maximum energy efficiency and product yield is crucial for their widespread adoption and environmental benefit. For pathways involving geological storage, long-term storage concerns present a critical challenge. While CO2 can be safely stored in deep geological formations, careful monitoring and management are essential to prevent leakage. The integrity of the storage site must be maintained over geological timescales, requiring robust regulatory frameworks and verification protocols. public perception and acceptance of geological storage also pose a challenge. Addressing concerns about potential seismic activity, groundwater contamination, and the long-term stability of storage sites requires transparent communication and rigorous scientific assessment. Ensuring public trust is vital for the successful deployment of large-scale storage projects. Finally, the environmental impact of certain utilization pathways needs careful consideration. While many CCU applications aim to reduce emissions, some, like enhanced oil recovery, can have complex life cycle impacts. The CO2 injected for EOR may be stored, but the resulting increase in oil production leads to further emissions when the oil is combusted. A comprehensive life cycle assessment is necessary for each CCU pathway to ensure a net environmental benefit. This includes evaluating the energy and material inputs for capture and conversion, as well as the emissions associated with the end use of the CO2-derived products. Avoiding unintended consequences and ensuring genuine climate benefits is paramount. In conclusion, carbon capture and utilization represents a promising and increasingly vital technology in the global portfolio of climate change mitigation strategies. Its ability to capture CO2 from diverse sources and transform it into valuable products offers a unique pathway to decarbonization and resource efficiency. The scientific and engineering advancements in this field continue to expand its potential. While significant challenges remain, particularly concerning costs, efficiency, and the environmental integrity of certain pathways, ongoing research and development are steadily addressing these hurdles. The integration of CCU with renewable energy sources and the development of novel conversion technologies are enhancing its viability and sustainability. Ultimately, CCU is poised to play a significant and indispensable role in the transition to a low-carbon economy. It offers a critical tool for industries that are difficult to decarbonize, provides opportunities for a circular carbon economy, and contributes to achieving ambitious climate targets. Continued investment, innovation, and policy support will be essential to unlock its full potential.